going to be a talk about some novel work we're doing trying to do interstellar observations of ices in a new way. So I brought this up before, but why ices? Well, of the 180 molecules detected in space, anything you want to make larger than methanol probably has to be made on a grain surface. So these are the places you want to look if you want to understand complex molecule formation. One of the problems we run into now is that these are the only molecules we have actually detected in an ice. These are the only molecules we've detected where we think they're frozen out and forming. Everything bigger and most of the other species are just not observed so far. And this is a big impediment to actually understanding ice chemistry, because interstellar observations are how we reconcile our theory with what's actually going on. And if we can't detect bigger, more complicated things, this is a problem. So we're a terahertz spectroscopy group, so we obviously want to try to solve this problem with terahertz spectroscopy. So terahertz is sometimes called the far infrared. It's very long wavelength infrared radiation, or verging on very high frequency microwave. It spans the two. And so the transitions you usually see here are either very low frequency, large amplitude vibrations from single molecules, or collective vibrations of solids. And it's the collective vibrations of solids we want to go after. And what we want to do is exploit the fact that it's very long wavelengths. So this is two optical images of disks, and you'll notice they're very fuzzy and opaque. So there's mass here. It's obstructing all of the optical photons. Dust is extremely opaque at optical frequencies. As you go lower and lower in frequency, the disk gets more and more transparent, and you can start seeing through it. But all the really interesting stuff in the disk, the ice especially, is all completely obscured because the outer edge of the disk is just blocking all of the light. And so this, I put this slide up before, but really quickly, this is really important because if we want to actually see into the really interesting parts of protoplanetary disks, the interesting stuff is happening in the midplane. That's where ice is freezing out. Ice freeze-out drives aggregation of small dust grains into bigger ones. In fact, ice is probably how you get over the centimeter problem. Building up bigger and bigger particles generally requires icy bodies. And it also, whoops, let's see if it's going to change. It also requires mass transport. So this is going to be what drives the composition of your planets and where all your organics end up and all your water. And the problem is, if you want to look at the midplane of the disk, you're only going to see very little in. So if you want to see in towards the center where the ice is actually freezing out, you need a way to look at it. So traditionally, the way ice observations are done is through absorption spectroscopy. So you have a star in the background, you have ice along the line of sight, and then you detect absorption of this. But the problem is, as you build up more and more dust in the line of sight, well, it gets opaque very quickly. At terahertz frequencies, though, the dust is completely transparent and light goes right through unless it's absorbed by the ice, or at least it's far more transparent. And the other thing that's very helpful is that you need a background star in the infrared. So to do an emission experiment to get ice to emit, you'd have to heat it up to several hundred Kelvin. If you heat an ice to several hundred Kelvin, the ice is evaporated already. So the only way to do it is absorption. So you have to find a place with ice and then a star in the background that hasn't desorbed your ice. So there's a very limited number of places we can actually observe ice in space. So that's the problem. We want to do this with terahertz, but the problem is terahertz spectra of ices in the far infrared don't really exist, or they're fairly limited. Turns out making terahertz photons is actually very difficult. So we go through a lot of trouble to make them. It's a big, complicated slide, but basically what we do is we take an ultra-fast laser, so a few tens of femtosecond long pulse. We focus it down to a point, and we generate a plasma. So this is our little plasma. It throws off a huge amount of optical light that's very pretty, but sadly we just block it. So it also gives off very intense, very broadband terahertz pulses. So these things span many hundreds of wave numbers all at once. And so what we're going to do is collect them and focus them through a substrate. There have already been a couple descriptions of how you make these, but our ice chamber is a small little HV system. It's a silicon substrate and a cryostat, so we can change the temperature from anything to about 10 Kelvin up to 300 if we want. And then we just dose in whatever ice we want to form, mixtures, layers, or just pure samples. And we deposit it on the substrate, and then just do a fairly simple Beer's law absorption experiment. We just look at the absorption through. And this is sort of the bandwidth of our instrument. So we can see everything from about a few wave numbers up to 250. And so now if we can do spectroscopy here, we need an observatory that can match that. And so I mentioned ALMA a little bit with the image of HL tau. It actually is pretty limited. It only covers the first terahertz of bandwidth we do. There's Herschel, Spire, and PAX, which have okay coverage, but these are actually now defunct. They're sitting at L2, but they're out of liquid helium, so they're not running anymore. There's only one observatory in the world that can cover the bandwidth we want, and that's Sophia's Fifi instrument. So to do sort of just testing, we've never done anything like this. The pretty obvious case is to go look at water. Water is the biggest component of any interstellar ice, so you'd like to start with water. So this is a spectra that Brett recorded of crystalline water ice at 10 Kelvin. It's nice and pretty. We get a very strong peak here. And if you look at the Fifi coverage, we have perfect overlap, except that right now Fifi is missing a filter, so we can't actually cover this range. And it's really sad. So just for a minute, I want to stop and tell you what Fifi is. It is an instrument hooked to the back of this telescope. It's on a 747. We fly it up to 40,000 feet and then open the door in flight and then use a 1 meter telescope in the back to track an object through turbulence. So it's got a massive system that keeps the telescope pointed even when the plane's jumping up and down. So we're able to track an object as we fly through the sky and get really nice data. So it's a really fantastic thing, but it doesn't quite work for water yet. What it does work for is CO2. CO2 is one of the next most abundant constituents in an ice, so it's another obvious place to go. So this is actually a spectra from Brett's thesis. We can make crystalline CO2 ice at different temperatures, and we have two very nice modes that pop up right in the middle of the Sophia band, so we can cover both. We also have this really interesting thing, which is the band position shifts with frequency, or with temperature. So anytime you observe one of these ices, you immediately know its temperature very precisely, and you get the information for free, which is very helpful for understanding the physics of whatever you're looking at. So we'd like to know what these are. It actually turns out to be very important to know what these two modes are. These are crystalline modes. So this is the low-frequency one. This crystalline CO2 ice bilayers moving back and forth between each other. This is just an optical phonon. And then the higher frequency one is, there we go, CO2 molecules, bands moving back and forth. And so it's really cool, but one of the issues here is that this requires crystalline CO2 to work. You have to have an ordered crystalline ice to get these modes to show up. So we can actually prove that. If we go through and make an amorphous ice, if we deposit an ice at 10 Kelvin where the molecules don't have enough energy to rearrange, you get this sort of amorphous mixture that can't crystallize. And if you try to take a spectra, you get a flat line. So this is good and bad for observations. It means that we're now sensitive to composition too. So once you heat an ice up, if you cool it back down, it'll stay crystalline. It will not lose that crystalline structure. But if it was never heated up, it will never make a crystalline structure. So this is good and bad because now we can track the thermal history of the ice. If you see a 10 Kelvin ice, but it's crystalline, you know at some point that ice was exposed to much warmer temperatures and then cooled off, and that can be very useful for understanding dynamics. The problem is, if an ice never saw a temperature warm enough to crystallize it, then the line of sight that has no CO2 or amorphous CO2 looks identical, and you can't tell if you have no CO2 there or if it's just not warm enough to crystallize. So this is the Fifi band. So this actually works out beautifully. Now the trick is that we want to go out and do something with this telescope that was never intended. So Fifi was meant for small, narrow spectral lines. Our lines are a few wave numbers wide. The lines that this instrument was intended to see were tenths to hundredths of wave numbers wide. It was never meant to see something this broad. It's an observing mode that was never tested. And so this is going to be tricky because, like I said, we're in a 747 at 40,000 feet bouncing around. Now, we fly that high to get above most of the Earth's water, but there's still a little bit of atmospheric water. So now you have a changing atmosphere and a bouncing telescope. And what you have to do is do 67 individual integrations across this band to get enough data to actually see this broad feature. And this is something nobody ever thought someone would try. And so this was totally speculative to see if if we could even get something that would be stable over the course of an observation. And so we proposed this to the Fifi instrument team, and they were surprisingly excited about it and really wanted us to give it a go. So we picked a target, NGC 7538. It's actually got two different sources. IRS-1, it's more processed and has very little CO2. That's going to be our reference source. We know from infrared observations there is no real CO2 ice there. And then we have IRS-9. It's dimmer, but it has very abundant CO2 ice, some of the most abundant CO2 ice observed in space. So what we're going to do is observe both of them back and forth simultaneously as we fly and see if we can actually get stable baselines. And so this is very new. We got this about a month ago from the Fifi team, so this just came down. So what we do, black and red are individual scans. So we started in the center and then worked out to the outside and then filled back in on the edges. And so each one of these is an individual scan. And this actually works surprisingly well for us. So all these big dips are atmospheric water absorption, but everything's tracking. So stuff we did 50 minutes after this follows the pattern exactly. Everything lines up nicely, and it's shockingly stable as we're bouncing around in the atmosphere. So this is a really promising start. It proves that we can actually get the telescope up there working and observe something this broad without having the atmosphere completely ruin the observations. We can do a background subtraction, and it's pretty clear that we don't correctly subtract out the water lines. So this is going to be the ongoing thing. This is something that's known in optical and infrared observations, is that atmospheric water subtraction is really tricky. The models that they have in the infrared are very good. So the next step is going to be starting to apply these methods to far infrared observations to really subtract the water out and get at the very weak absorption features that we hope are here. All right, with that, I'd like to thank the rest of the Blake group, our funding sources, and you guys for your attention. So, questions?
Really exciting work. So I was just wondering if Herschel PAX covers the same spectrum.
Herschel PAX covers some of the same spectra. So there's archival data, and Thomas Henning's put up a slide where he shows that water ice absorption. The calibration is really tough, so we're going to be working with them a lot to figure out, because PAX and Fifi are identical instruments. Fifi exists because they built a backup of PAX, and they just had it laying around, and so now they put it on a telescope.
People.
Yep, it's on.
Okay, I know people working on Herschel digit PAX data. They're trying to calibrate it. I don't think they trust the ice calibration yet, but it's getting there soon.
Yeah, so Thomas Henning's got a little bit, but yeah, this is a tricky process. This is not what this instrument was designed for. So calibration is going to be really important going forward.
All right, well, yeah.
Yeah.
Do we just have the lights on the dim?
Unfortunately not. It's either going to be pitch black in here or like this. We can take a vote, but I figured people don't want to fall asleep. Sorry. All right, let's thank Brandon again before we move on.